Hello everyone, this is going to be a pretty simple laid-back chill video. We will be solving the Schrodinger equation for a free particle potential. The free particle potential is defined as the case for the potential equals zero. So there are no forces, well, there are constant forces really, acting on the particle. So let's solve it. Okay, so this means, so here is the Schrodinger equation. So if v equals 0, that means that we have this. Okay, so now we can multiply both sides by 2m over h bar squared minus so now we have that the second derivative of psi with respect to x equals minus 2me over h bar squared psi. Since this is a second order derivative, it motivates us to define 2me over h bar squared as some constant k squared, where k is defined as the square root of 2me over h bar. So second derivative of psi with respect to x equals minus k squared psi. So we can add both sides by minus k squared to get this relation over here. This is a non-homogeneous linear second order differential equation, which means that psi of x it's homogeneous, not non-homogeneous. So psi of x can be written as a exponential e to the rx. So this means that r squared e to the rx plus k squared e to the rx equals 0, which means that we can factor e to the rx out. That equals 0, which means that r squared plus k squared equals 0, which means that r squared equals minus k squared, which means that r equals the square root of minus k squared, which is just ik or minus ik. So you can take superposition of these. You have a e to the ikx plus b e to the minus ikx. Okay, and this is our answer. We don't have any quantization over here, since we had no boundary conditions, no normalization conditions, or blah blah blah. But here is our solution. So one might ask, what are the values for a and b? Well, we can't actually find those values since this is not a real physical state. Like, you can't normalize it at all, right? Like the integral to infinity of psi dx is infinity, which means that psi does not exist in a Hilbert space. L2, L squared. It's not non-normalizable. Because there's no boundary conditions. I guess the end anywhere. So that's pretty much it. It's impossible for a particle to be in. It's impossible for a free particle to be in the stationary state, psi of x. This is like k of x. Oh yeah, also k is a continuous variable, since there's no quantization, and we can find that E equals h bar squared k over 2m. If you can prove that yourself, it's not that hard. You just derive it from the formula of k. What's also interesting is that if we take a to be 1 and b to be 0, which is like a equal 1 and b equals 0, then you have psi of x equals a e to the ikx, right? And this actually is an eigenstate of momentum, which is actually pretty cool. Here is a demonstration. Is a demonstration. So remember that this. So to be an eigenstate of momentum, this must follow, and p hat is minus I h bar partial over partial x, or d over dx. So minus I h bar d over dx of e to the ikx should equal p times e to the ikx. So minus I h bar times first derivative of that is just going to be ik e to the ikx equals p to the ikx. I times I is minus 1. Minus 1 is just 1. So h bar k e to the ikx equals p to the e to the ikx, which means that P equals h bar k. So here we have the momentum eigenvalue, just h bar k, which means the momentum is also continuous and it's also definite, which means that it's not only an eigenstate of position. I'm sorry, of energy. It's an eigenstate of momentum. Yeah. So again, stationary state of the free particle cannot be normalized. However, we can take a superposition and normalize that. So normally, some superposition is just Cn psi n. But in this case, n is not continuous and it's a k instead. So like k is a continuous variable, right? Like in a normal case, in the discrete case, we have C1 psi 1 plus C2 psi 2 all the way to like Cn psi n, right? Or n is the number of dimensions in your space. But in this case, n isn't discrete. Like k is continuous, right? So we'd have like C1 psi 1 plus like C1.00001 psi 1 plus C1.000. Like you're adding like the intervals is not an integer. The separation of your intervals is an infinitesimal, right? So this sum takes the form of an integral. Sorry if that's a bit like handily sloppy. What I'm just trying to make you guys understand is that since like we are adding in like a number of eigenstates and the separation of those eigenstates is continuous, then the sum is an integral instead. So instead we have psi of x, the general psi of x, is an integral, is a sum for k of ck psi k, but really it's an integral of it's an integral with ck becoming phi k instead. Psi k, that is psi of x. So psi k of x. Yeah. And k like is like all continuous values. So yeah. What now? So remember that psi k of x, we can take a to be 1 and b to be 0. We can just choose that. So psi of x is integral of phi k e to the I kx. And this is actually just a Fourier transform, right? Which means that phi of k equals the integral of psi of x e to the minus I kx. I think like it's dx and here's dk, I think. You can prove this yourself by just like writing it in the abstract algebra form. Not abstract algebra, but like the abstract form that is algebra. And we can solve for phi k that way. So yeah, and psi of x can actually be normalized, even though the stationary states are not normalized. And it turns out that phi of k, p is h bar k, right? So phi of k is also phi of momentum over h bar. So you can really say that, and you can see that this is really e to the I px over h bar. So we can say that it's a superposition of the momentum eigenstates e to the I px over h bar. If that makes sense. Kind of like jibber jabbering right now, but yeah, that's like the solution to the free particle potential.